So, once again welcome back. I am sure till the almost for the 40 total number of lectures which would be given for this course, we are almost at the penultimate stage where about 3 classes are left. And we had in the last class we had just started about the value at risk concept. It is basically a measure of risk. Like as you know, I did mention about conditional value at risk, that is also a measure of risk. I did mention you that conditional value at risk is the center of gravity of the overall distribution, considering that it is a loss distribution on the right hand side of var. It means you find out the expected value of that. And then we also did discuss in a very simple way the concept of standard deviation, concept of beta, concept of other risk measures. In the swaps and also we did discuss, and how the risk concept would be brought into the picture. So, continuing our discussion with value at risk, this basically means that if you consider the last slide which we closed in the last class, it means that the value of the portfolio would now loss would become more than 158,114, considering the level of confidence or number of days of var you want to have for your problem. Simplistically, again with repetition I am measuring that if you want to find the var for more number of days, obviously you have to multiply by the square root of t or multiply it by t, depending on whether it is standard deviation you are looking at or you are basically looking at the variance. So, that was basically the var which you had calculated was 158,114 for, and if you consider 99% var, it will basically give you the 6 sigma deviation, 3 plus and 3 minus over and above the mean value. So, the var value comes out to be 2.38 into that value which you calculated, it is 158,114, that comes out to be about 3,68,408. Now, if you want to find out the 95% confidence level var, then obviously what you will do, rather than take 2.33, you will multiply it by the corresponding value of the variable of k. If you want to find out 99%, again you will multiply by a corresponding value of k. So, what we mean by that k is this, again I am reiterating, this is the normal distribution. So, if you go 6 sigma, which means 3 sigma here, 3 sigma here, then you have to basically multiply by 2.33. If you go 4 sigma, that is 2 sigma onto the right, 2 sigma on the left, or 2 sigma, that is sigma to the left and sigma to the right, then the corresponding values can be found out from the standard normal deviate, based on which you can find the overall area. Now, this is the corresponding picture which I want to discuss. So, it is basically 2.33 or plus 2.33, whichever direction you are considering. So, 2.33 would basically have a counterpart plus on the right hand side. Similarly, 1.65 and 1.28 would be the corresponding values of 95% and 90%. So, if you are considering 99%, then the overall area left would be 0.01. So, 0.01 would be basically, if it is a two side, if you consider the very simple example, a hypothesis testing. And when, if you remember, we have done the hypothesis testing of these cases where alpha and betas were there. So, generally if it is two sided tail test, you will have basically equal proportions being divided of the total 1% area, that means 0.05, 0.05 onto the right or the left. Similarly, it was 90%, so 10% would be divided by 5% and 5% onto the left, right and the left. But now, in the var case, you are only interested to find out the overall risk or overall loss you are facing for either the left tail or the right tail, depending on what you are trying to basically specify. Generally, if you want to specify the losses, then obviously the losses or the gains, it can be the other way around also, the gains. So, obviously losses would increase on the right hand side if you are doing that nomenclature one. That means losses are more on the right hand side and losses are less on the left hand side, which means profits are more on the left hand side, profits are more on less on the right hand side. So, obviously you can do the nomenclature accordingly, but in this problem if you see, the overall var values would be given here for 90%, for 95%, for 99%, and the overall area which you are considering, based on which you will predict the overall loss, is given on the left hand side of this diagram. That means losses are increasing in the monetary sense, more as you go on to the left, and if you go on to the right, it will be gains. So, similarly, you can have the diagrams like this, where this is 90%, 95%, 99%, where the losses are increasing in the value terms on to the right, while on the left the losses are decreasing. So, whichever nomenclature you follow, be very careful that how you are trying to basically draw the losses and how you are trying to basically draw the value of VAR based on which you are trying to find out the overall risk. Note 2.33 means there is 1% probability that a normally distributed variable will decrease by more than 2.33 standard deviations on to the right or on to the left, depending on how you are trying to draw the overall loss. 1.65 means that there is 5% probability that a normal distributed variable will decrease by more than 1.65 standard deviation on to the right or the left. Similarly, plus or minus would basically come into the picture, that is minus 1.65 or plus 1.65, or it will be minus 2.33 or plus 2.33, whichever nomenclature you are using. While 1.28 means that there is 10% probability that a normal distributed variable will decrease by more than 1.28 standard deviation on to the left or the right, as the case may be. Assume the volatility of TISCO is 3% per day, and also consider a portfolio consisting of 5 lakh in shares of TISCO. So, these shares which I am considering does not mention whether they are options, whether they are stocks, whether they are bonds, whether they are swaps, whatever. I am just collectively considering them as the portfolio. We are interested to find the VAR for 10 days at different confidence levels. So, this is 3% per day VAR. So, find the VAR at 99% confidence. The answer is 1,10,527. So, what you have to do is that this is 3% per day and the value of the portfolio is given. So, what you will consider is that per day has to be converted if you are finding the VAR at 10 days. So, it would be multiplied by square root of 10, because you are considering only on the standard deviation. It was variance. So, obviously, it would be multiplied by 10 only, and then considering the actual formula, you can just find out the VAR values as it is given. So, here it will be multiplied by 2.33, here it will be multiplied by 1 point and 1.65 and 1 point, let me check, 1.28, 1.65, 1.28 and 1.65 as the case may be, and you can find out the VARs accordingly. Now, we will now consider two assets. So, till now we were only considering a portfolio which was considered as a single asset. So, the word which I mentioned just few minutes back, that we would not consider what is there in the portfolio, whether it is an option or a swap or different type of stocks, we are not going to differentiate that. We only consider that as a block, and based on that we found out the VAR. Now, what comes into the mind is that what we have a portfolio and we want to find out the VAR of the total portfolio, given the VAR for each and every individual financial asset which is in the portfolio. So, that is the main concern, considering that we have understood the concept of VAR in a little bit more objective manner. So, now we consider two assets, only two, it can be increased to n also, two assets which comprise the portfolio. Then the natural question is, how do we calculate the overall VAR? The corresponding VAR has to be found out, but when you want to find out the VAR, obviously the question would come that if there are two assets, they are random. If there are two assets which are random, then obviously it will mean that there would be a covariance variance matrix also there between these two assets, which will be of size 2 cross 2. Answer is right. We have to use that concept in order to find out the overall covariance of the portfolio. So, this is how you do, and we have already covered that topic, considering that you are doing the portfolio optimization problem in the first few lectures. So, now we consider the covariance variance being given for two assets is given by this formula, where the first is the covariance of the first asset with itself, which is the variance. Third term is the covariance of the second asset with itself, which is the variance, while the middle term, which is the of the diagonal element multiplied by twice, is basically the covariance existing between x and y. So, basically you have the overall covariance given, and once the overall covariance is given, if you go back to the actual formula, this the VAR value which was given considering 2.33 standard deviation or 1.65 or 1.28, depending on the level of confidence you want to have, you can definitely find out the VAR. But there are few pitfalls which are going to be mentioned very categorically to all of you. So, let us first complete the problem in a very simplistic sense, then I will come to the pitfalls. Let us continue the example. We will consider that as before the overall correlation existing between these two assets is 0.75. Hence, to find out the VAR for the portfolio, we first find out the 10-day change of the portfolio due to the individual volatilities, which will be given by this. So, this is 10-day. So, basically this is being multiplied by square root of 10, and these values which you see, this is sigma square. So, obviously sigma square would mean that the value of standard deviation which you have for the first asset is this, value of the standard deviation of the second asset is this, while this is 2 into variance, this is the correlation coefficient which is 0.75 into the values which you have is this. So, these is the standard deviation of the first multiplied by the standard deviation of the second, but only fact being very important to note is that you will always multiply it by the square root of 10, considering that you want to find out the VAR given the VAR is given for 1 day. So, thus the VAR at a 99% confidence level is found out by multiplying the value which you have found out here by 2.33. So, similarly if you want to find out the VAR at 95% confidence level, 90% confidence level, you can find it accordingly. Similarly, just before I go to the next slide, you have a question that you want to find out the VAR for more than 2 assets. What will you do? You will follow the same, exactly the same principle. Have the variance covariance matrix. So, this is sigma 1 which is the variance of the first, which is the covariance of the first with itself. Sigma 2 is the covariance of the second with itself. Sigma 3 is the covariance of the third with itself, and these are the covariance values between 1 and 2 or 2 to 1. This is between 1 and 3 and 3 to 1, and this one is basically 2 to 3, 3 to 2. So, these are basically symmetric, that is why you have been multiplying by 2. So, again you follow the same fundamental principle. If you have the VAR for 1 day, you want to find out the VAR for 10 days, multiply them by the square root of 10, which is an important factor which I am trying to stress time and again. Now, the pitfalls which I mentioned. Generally the properties of any risk measures, now I am making a very general statement and it is very important in finance. The properties of any risk measures, be it beta, be it standard deviation, be it correlation, be it the value of VAR, be it the value of conditional value of risk, whatever you have, they should basically have 4 properties. One is the positive homogeneity, which means that if you multiply the overall, so I am not going to the mathematical terms, I am basically explaining it from the qualitative point of view, then coming to the quantitative point of view. So, if you see the first formula, the positive homogeneity, it means for any delta value, that means any increase and decrease of the overall portfolio value or overall value of the asset which you have in your basket, or you want the portfolio you want to formulate, if that can be formulated by a single asset, that the single smallest unit of the asset, and if you find out the risk of that and multiply it by the number of times it will decrease or number of times it will increase, that will basically give you the overall value of the risk measure, which if the property holds, then the property of positive homogeneity is true, which means I have one asset and I have the standard deviation of that. Now, in the second instant I say that I take such one asset 10 number of times. So, lambda would be 10. So, if I find out the variance, covariance, or say for example whatever risk measure I have, and rather than basically finding out for all of them 10 collectively, what I do is that I take one of them, find out the variance, covariance or whatever risk measure is there and multiply it by 10. So, if there is a 1-to-1 correspondence, that means that it can either be increase or decrease and the exact value of the risk measure can be found out, then the positive homogeneity property holds true. That means there is a linear relationship between increase and decrease. Second point is the sub-additivity, which is very important. Consider that you have 2 different financial assets and you have some measure of risk. Now, rather than finding out the collective combination of these 2 assets and then finding out the risk, another nice thing which can be done is that find out the individual level of risk, which is this rho x or rho y, and if you basically add them, considering there is an additivity between them on the left hand side, which means adding the risk values of two different assets when combined should definitely give you the collective risk of the portfolio, where the portfolio now consists of those exact two assets in the same proportion. In case if I say for example, there are three different individual assets and I want to find out the risk of all of them three individually, then if I combine them, then the combined risk of all of them three combined together is exactly the risk of the portfolio which would be there if the portfolio consists of those three assets combined together as one unit. Now, this property of this sub-additivity means that adding or subtracting of this financial risk of two or more different type of financial assets should hold true whatever the distribution is. But the caveat or the important point is that this only holds true for the case when you have normal distribution or a class of utility functions which are quadratic in nature. Now, if you remember very clearly, I had mentioned that in the beginning of the class, and I did mention one or two points later on also, that utility functions being quadratic, which would imply that the returns being normal would have a huge amount of simplification and overall understanding of the overall portfolio in a very simple sense. Now, standard deviation which you are using, variance which you are using, VAR you are using, that sub-additivity property for those risk measures would hold if and only if they are symmetric distributions or normal distribution. In case you have non-symmetric distribution or extreme value distribution, then these properties, if you are considering these sort of risk, which is VAR, which is standard deviation, which is variance, would not hold true. But if you ask the question, will these property hold true if we consider this extreme value distribution or asymmetric distribution for the conditional value at risk? The answer is yes, because conditional value at risk basically follows all the four properties which we are going to discuss, two of them which we have already discussed, which is positive homogeneity and sub-additivity. The next one is monotonicity, which means that if there are two different assets in different proportions, then or if the overall risk measure, so called risk measure, whatever it is, if you think the overall risk measure of the one asset is less than the other, then this property of monotonicity would also hold true for different combinations of the assets you are going to take. This property also does not hold true for the VAR, standard deviation and variance if you consider any distribution which is non-normal, but it holds for the property of CVAR even if you consider non-normal distribution. So, that is why if you see the point 2 and 3, when you refer to the slides, they are marked in bold, which means these two are very important properties which should hold for any risk measure, but it does not hold for the case of VAR in case the distributions are non-normal. The transitional invariance property basically means that whenever you add or subtract a certain proportions from your assets in terms of risk free interest rate is basically a simple addition and subtraction which is going to take place for your overall risk measure. This property generally means that if you remember in one of the problems we consider the ratio of the excess return divided by beta or excess return divided by sigma, which means that you are trying to basically analyze your problems from the excess amount you will get from any particular asset, considering that you are doing a benchmarking with the risk free interest rate. So, which means that any one of the risk measures whichever you are considering, whether it is CVAR, whether it is standard deviation, whether it is basically beta, whether it is conditional value to this VAR value VAR which you are using, should basically have that property such that you will always peg your actual asset or a portfolio with respect to risk free interest rate. So, amongst all these four, which are the general properties of risk measures, the second and the third are very important, which should be noted that for VAR they do not hold true considering the fact that the distribution is non-normal. Now, coming to the first property basically means what I actually mean technically is a combination of the first and the second in this slide. The first property means that the risk for a portfolio consists of two or more assets should be less than the additional value of the risk which we already have done. How we have done? The question is, you remember we have done diversification, which means that more you basically put your risk in different baskets, the overall combined risk basically decreases for the overall collective portfolio. This property may not hold true if you have a non-normal or asymmetric distributions, remember that. And the second simply states says the second property means that the more the return is, more would be the risk. That means, there is a commensurate one to one correspondence, may not increase in the same proportion, but this property also does not hold true for those class of risk measures, one of them being var, in the case the distributions are normal or asymmetric distribution. So, with this I will close today's class and continue the more discussions more in the next class, which would be considering the credit matrix and the different concepts of R. Thank you.